Hello children, once again welcome back to Physics with Sanoop. In this video we will be discussing all previous questions from the chapter Ray Optics and Optical Instruments. Please do watch the videos with a pen and paper and also note down all the important points and also solve with me. Okay, now see, first question: an object is placed on the principal axis of a concave mirror at a distance of 1.5 f from the mirror. See, the center of curvature is at a distance 2f from the mirror and focus is at a distance f from the mirror. Here the object is kept at a distance 1.5 f from the mirror. Means between the focus and the center of curvature. See, when an object is kept between the focus and the center of curvature, image will be formed beyond the center of curvature. Okay, so image will be formed somewhere here beyond the center of curvature. See, in optics, if the image distance is more than the object distance, if the image distance is larger, image will be bigger. If the image distance is smaller than the object distance, then the image will be smaller than the object. Okay, here the object is kept between the focus and the center of curvature, so we can expect the image beyond the center of curvature. See, if the image is formed in front of a mirror, it will be real. All the real images will be inverted provided it's formed by a single optical element, means a single mirror or a single lens. Then if the image is real, it will be inverted. Okay, now see, in case of a mirror, the images formed in front of the mirror are real. Images formed behind the mirror are virtual. Okay, now see, here we have the law of distances for a spherical mirror, 1 by u plus 1 by v equal to 1 by f. See, in this law of distances we have to follow a sign convention. You need not by heart any statement in this sign convention. It is very simple. See, it's called new Cartesian sign convention because it is just like Cartesian coordinate system. See, what is Cartesian coordinate system? It is nothing but the xy coordinate system. Okay, now see, you have to choose the pole just like x and y axis. Okay, the point of intersection of x and y axis will be the origin. Okay, here this pole is to be chosen as the origin. All the distances towards right, positive, towards left, negative. All the measurements should be starting from the pole. Okay, now the distances measure upward positive, downward negative. Okay, that is new Cartesian sign convention. Okay, so here the object is kept in front of the mirror, means the object distance will be from the pole to the object. So it is negative object distance. Okay, image distance here, see, here we have to locate the image. We have to find the image distance. See, the quantity that you are going to determine, going to find out. You should not give any sign to the unknown quantity. Okay, you put or you substitute all the given quantities in proper sign, then you will get the unknown quantity in proper sign. Here u is given, f is also given. So you put the values of u and f in proper sign, then you will get v in proper sign. Okay, so here we have u as negative and focal length is negative for concave, whether it is a lens or mirror. If it is concave, focal length is negative, and if it is convex, focal length is positive. Here we have a concave mirror, so its focal length will be negative. Object distance, as the object is kept in front of the mirror, object distance will be measured from the pole to the object left side towards left, so object distance will be negative. Okay, so u equal to 1.5 f means it is 3 by 2 f and I have taken it as negative. Okay, from here we will get 1 by v equal to 1 by f minus 1 by u. F is negative, so 1 by minus f, it will be minus 1 by f. Minus 1 by u, see, u is 3f by 2. So 1 by u will be 2 by 3f and it is negative also. So minus 1 by u means minus 2 by 3f. So this minus will become plus. So minus 1 by f plus 2 by 3f. It will be minus 1 by 3f, or we will get minus 3f. What is the significance of that negative sign? See, the image is at a distance 3f from the mirror and it is towards the negative side, means towards left side. So the image will be formed at a distance 3f from the mirror towards left. Okay, so we have image distance is equal to 3f. Okay, match the corresponding entries of column 1 with column 2. Okay, where m is the magnification produced by the mirror. See, a convex mirror always form virtual, erect and diminished image, whereas a concave mirror can produce real image as well as virtual images. But a concave mirror can produce a virtual image only when the object is kept between the focus and the mirror. That virtual image will be magnified. Means, if the virtual image is formed by a concave mirror, it will be definitely magnified. If the image is formed by a convex mirror, it will be virtual, it will be erect, it will be diminished for all positions in front of the convex mirror. Okay, now let's try. First, m equal to minus 2. Magnification negative means image is real and it is inverted. So here we have m equal to minus 2. It means magnification is negative, means the image is real. It must be formed by a concave mirror. Okay. So real image and concave mirror. So P must be matching with B and C. Okay. P must be matching with B and C. Fine. And the next case we have magnification equal to minus half. Again, magnification is negative, means image is real. It can be formed only by a concave mirror, because here we have only two options, concave mirror or convex mirror. Convex mirror always form virtual image. Here we have a negative magnification, means the image is real, means it must be formed by a concave mirror. Okay, and it is a diminished image because the magnification is half. Okay, so it is a real and concave mirror, so it must be matching with B and C, Q. Okay, and next C, this R, M equal to plus 2, means magnification positive, means image is virtual, and it is 2 means magnified image, virtual and magnified. Convex mirror always form virtual image, but it will be always diminished. Here we have a virtual image, but it is magnified. It can be formed only by a concave mirror. Okay, so mirror is concave, image is virtual. So must be matching with B and D. R must be matching with B and D. Okay, and finally we have M equal to plus half. Means it is a virtual image and it is diminished. It must be formed by a convex mirror and the image is virtual. Okay, so convex mirror A and virtual image D. So S must be matching with the A and D. Okay, so P with B and C. Here we have P with B and C. Q also with B and C. R with B and D, and S with A and D. So this is the correct option. A rod of length 10 cm lies along the principal axis of a concave mirror of focal length 10 cm in such a way that its end closer to the pole is 20 cm away from the mirror. Okay, the length of the image is, see, the focal length is 10 cm and a rod is kept along the principal axis of the mirror. Its nearer end is 20 cm away from the mirror. 20 centimeter away from the mirror means at the center of curvature. Okay, so this is the point C, center of curvature. Okay, and a rod of length 10 centimeter is kept like this, and that rod is AB. AB is the object. It is the rod of length 10 centimeter, and its nearer end, that is the point B, is at a distance 20 centimeter from the mirror, means it is at the center of curvature. See, when an object is kept at the center of curvature, image will coincide with the object. Okay, so we have B and its image, let us represent B dash. See, in optics we can find the images of point objects only. We have an object AB. How do we find the image of that object AB? We have to consider these n points A and B as two separate point objects. Find the image of A as A dash. Find the image of B as B dash. then you join A dash and B dash. That is the procedure to find the image of extended objects or the image of any object other than a point object. Okay, so the point object B, here it is kept at the center of curvature, so its image also will be formed at the center of curvature. So B and B dash coincides. Okay, now consider A as a point object. Okay, now see, from the pole up to the point B, the distance is 20 centimeter, and from B to A, that is the length of the rod, and it is equal to 10 centimeter. So from the pole to the point A, distance is 30 centimeter. Now consider point A as an object. Its object distance U equal to 30 centimeter, and as it is measured towards left, we have to take it as negative. Okay, so the image of this point object A will be formed by the mirror, and its focal length is given as 10 centimeter. So let us apply 1 by V equal to 1 by F minus 1 by U. Okay, and 1 by V equal to 1 by F equal to minus 10 because it is a concave mirror, minus, and 1 by U is minus 30. So it will be minus 1 by 10 plus 1 by 30. This minus 1 by 10 can be written as minus 3 by 30 plus 1 by 30. Minus 3 by 30 plus 1 by 30. So it will be minus 2 by 30. Minus 2 by 30 means it is minus 1 by 15. So 1 by V equal to minus 1 by 15. So V equal to minus 15. V, see, that is the image distance of the point A. Means from the pole to the point A dash. A is the object, A dash is its image. So the image of the point A will be formed at a distance 15 centimeter from the pole. Okay, so let me represent A dash here. Okay, see, from the pole up to the focus, the distance is 10 centimeter. From the pole up to the center of curvature, it is 20 centimeter. So 15 centimeter will be in between. Okay, so I have marked A dash here. Okay, so that PA dash equal to 15 centimeter. We have to find the length of the image, means A dash B dash. See, PA dash is 15 centimeter. And PB dash means from the pole to the center of curvature, it is 20. Okay, so A dash B dash equals PB dash minus PA dash, means 20 minus 15, that is equal to 5 centimeter. So the length of the image is 5 centimeter. And light travels a distance x in time t1. Okay, in time t1 in air. So the speed of light in air will be distance by time x by t1. And it travels a distance 10x in time t2 in another denser medium. So the speed of light in that medium will be v equal to 10x by t2. And sine c, where c is the critical angle. Sine of the critical angle is reciprocal of the refractive index, and it is equal to v by c. Speed of light in the medium divided by speed of light in vacuum, or here it is the speed of light in air. So 10x by t2 divided by x by t1, so it is 10 t1 by t2, that is sine c. So c, critical angle will be sine inverse 10 t1 by t2, so sine inverse 10 t1 by t2. A light ray falls on a glass surface of refractive index root 3 at an angle 60 degree. The angle between refracted and reflected rays would be. See, here we have the refractive index as root 3 and angle of incidence as 60 degree. What is Brewster's law? When mu, refractive index equal to tangent of the angle of polarization. Okay, mu is root 3 and angle of incidence is equal to 60 degree. If mu is root 3, angle of polarization will be 60 degree and the light is incident at 60 degree. Means light is incident at the angle of polarization, or light is incident at the Brewster's angle. When light is incident at Brewster's angle at the surface of a medium, then the reflected and refracted rays will be perpendicular to each other. Okay, here the angle of incidence is equal to Brewster's angle 60 degree. Okay, then a part of the light will be reflected and the rest will be refracted. If the angle of incidence is equal to Brewster's angle, then reflected and refracted rays will be perpendicular to each other. And we have to find the angle between refracted and reflected rays. It is equal to 90 degree. Okay. Now see next, two transparent media A and B are separated by a plane boundary. The speed of light in those media are 1.5 into 10 raised to 8 and 2 into 10 raised to 8 meter per second respectively. The critical angle for a ray of light for these two media is sin C equal to 1 by mu, where mu is the refractive index of denser with respect to rarer medium. So sin C equal to 1 by mu, where mu is the refractive index of denser with respect to rarer. So 1 by mu, that will be equal to speed of light in the denser medium divided by speed of light in rarer medium, and it is 1.5 into 10 raised to 8 divided by 2. It is equal to 0.75. So critical angle will be sin inverse 0.75. Okay, sin inverse 0.75. Which of the following is not due to total internal reflection? Working of optical fiber is an application of total internal reflection. Difference between apparent and real depth of a pond, that is the application of refraction. Okay, mirage on hot summer days, it is due to total internal reflection. Brilliance of diamond, of course, total internal reflection. A ray of light traveling in a transparent medium of refractive index mu falls on a surface separating the medium from air at an angle of incidence 45 degree. For which of the following value of mu the ray can undergo total internal reflection? See here, the angle of incidence is 45 degree. In order to occur total internal reflection, angle of incidence, that is 45 degree, must be greater than critical angle. So 45 greater than critical angle. See, when theta is more, sin theta will be more. So sin 45 greater than sin C. Okay, let me take this sin C to the left and sin 45 to the right. So 1 by sin C greater than 1 by sin 45. 1 by sin C is the refractive index. That should be greater than root 2. Okay, that is the condition for the total internal reflection here. Root 2 is 1.414. So the refractive index of the medium should be more than 1.414 root 2. Okay, here it is only 1.4, here it is only 1.33, this is 1.25. So there is only one value that is greater than root 2, that is 1.5. Okay. Now let's see what we have next. The frequency of light wave in a material is 2 into 10 raised 14 Hertz and the wavelength is 5000 angstroms. The refractive index of the material will be. See, refractive index of the material equals speed of light in vacuum by speed of light in the medium. See, speed of light in vacuum is C, that is equal to 3 into 10 raised to 8. And speed of light in the medium, we can write nu lambda. Nu is the frequency and lambda is the wavelength. Frequency is given as 2 into 10 raised to 14 Hertz and wavelength is 5000 angstroms. See, 1 angstrom equal to 10 raised to minus 10 meters. So 5000 into 10 raised to minus 10. And see, this we will get it is equal to 3. So the refractive index will be 3. Okay. And next, a small coin is resting at the bottom of a beaker filled with a liquid. A ray of light from the coin travels up to the surface of the liquid and moves along its surface. Along its surface means, see, a ray incident like this, see, goes like this. Means this angle must be the critical angle. Okay, because this is 90 degree. Okay. Now, a ray of light from the coin travels up to the surface and moves along its surface. How fast is the light traveling in the liquid? Means we have to get the speed of light in the liquids. Okay. See, we have a right triangle here. See, this one is a right triangle. This is 4 centimeter. This is 3 centimeter. So by Pythagoras theorem, we will get 5 centimeter this one. Okay. And as this angle is a critical angle, okay, so this must be this also critical angle. Okay. And sin C will be see from this triangle, sin C will be 3 divided by 5. Okay, sin C equal to 3 by 5. Actually, sin C, sine of the critical angle, equal to speed of light in the medium divided by speed of light in vacuum. Okay, and sin C we have got 3 by 5. Speed of light in the medium we have to find out. Speed of light in vacuum is 3 into 10 raised to 8. So from here we will get a V equal to 3 into 3. See, V equal to, this is 3 into 3, that is 9, okay, into 10 raised to 8 divided by 5. Okay, 9 by 5. 9 by 5 means 18 by 10, or this is equal to 1.8 into 10 raised to 8 meter second raised to minus 1. 1.8 into 10 raised to 8 meter second raised to minus 1. Okay. The reddish appearance of the sun at sunrise and sunset is due to, it is due to the scattering of light. It is due to the scattering of lights. Okay, and next, an air bubble in a glass slab is 5 centimeter deep when viewed from one face and 2 centimeter deep when viewed from the opposite face. The thickness of the slab is. See, when an object in a denser medium is viewed from rarer medium, it appears to be closer than it actually is. Here we have the air bubble, and its actual distance from one side is x, and its actual distance from the other side is, opposite side is y. Okay, so when that air bubble is viewed from this side, it appears to be at, say, x dash. Then x is the real and x dash is the apparent. Real by apparent will give you the refractive index. Means x by x dash will give you the refractive index mu. So the real distance x is mu times the apparent distance x dash. See, when viewed from one side, it appears to be at 5 centimeter. Means that 5 centimeter is the apparent distance, or it is x dash. Similarly, from the other side, we will get y equals mu y dash. Okay, so what would be the thickness of the glass? It is x plus y. Okay, and x plus y we will get mu times x dash plus y dash, where x dash is the apparent distance from one side and y dash is the apparent distance from the other sides. And x dash and y dash are given as 5 centimeter and 2 centimeter. So this will be 5 plus 2, that is equal to 7. So mu times 7, 1.5 times 5 plus 2, that will be equal to 10.5 centimeter. Okay, 10.5 centimeter, right? Now, one face of a rectangular glass plate 6 centimeter thick is silvered. An object held 8 centimeter in front of the unsilvered face forms an image 12 centimeter behind the silvered face. The refractive index of glass is. When an object in a denser medium is viewed from rarer medium, it appears to be closer. Okay, now see this AB. See, this is the actual position of the mirror. But when it is viewed from this side, it appears to be closer. Okay, it appears to be here, right? And see this distance. Let me represent it as S. It is called a shift, and for that shift we have a beautiful formula here. S equal to D, it is the actual thickness of the slab into 1 minus 1 by mu, where mu is the refractive index of the slab. D is the actual thickness. See, the total thickness of the slab is 6 centimeter, and see this side is silvered, so it will appear as a it will act as a mirror. And when that mirror is viewed from this side, it appears to be closer by S. It is called a shift. Okay, so this distance will be 6 minus S. 6 minus S. Okay, and this is the apparent position. See, this is the apparent position of the mirror. See, in case of a plane mirror, image is formed as far behind the mirror as the object is in front of it, or the object and image will be equidistant from the mirror. Okay, see, this is the position of the mirror. Okay, and the distance of the object from this mirror will be 8 centimeter plus 6 minus S. 8 plus 6 minus S means 14 minus S. Okay, that is the distance of the object from the mirror. Okay, distance of the image from the mirror will be, this is S and this is 12. So 14 minus S equal to 12 plus S. Okay, take take this minus s to the right, it will become s plus s, 2s, and 14 minus 12 will be 2. Okay, so yes, we will get 1 centimeter, that is the shift. Okay, and see in this expression for the shift, you can put d equal to the thickness of the slab, and it is 6 centimeter, and s is 1 centimeter. Okay, so we will get this s by d, and 1 minus 1 by mu equal to s by d, and 1 by mu will be 1 minus s by d. S is 1 centimeter and d is 6 centimeter. So 1 minus 1 by 6, that is 5 by 6. It is 1 by mu. So mu will be 6 by 5. And 6 by 5, it is 12 by 10 equals 1.2. Okay. So 1.2, that is the refractive index. Okay. Now a point source of light is placed 4 meter below the surface of water of refractive index 5 by 3. The minimum diameter of a disc which should be placed over the source on the surface of water to cut off all light coming out of water is. See, when a point source is kept under water, then the light will come out of the water surface only through a circular area, and the radius of that circle through which the light comes out is given by r equal to d divided by root of mu square minus 1, where d is the depth of the source and mu is the refractive index of water if it is kept below water. Okay, and here mu is 5 by 3, so 5 square by 3 square minus 1, so r equal to 4 by 16 by 9, and that is equal to 3 meter. Okay, 3 meter, that is the radius, but we have to find the diameter. See, the minimum diameter of a disc must be 6 meter. Okay. Next, time taken by sunlight to pass through a window of thickness 4 millimeter whose refractive index is 3 by 2. Okay, here I am using t for the time and x represents the thickness. So time equal to mu x by c. Mu is 3 by 2 and x is 4 millimeter, means 4 into 10 raised to minus 3 meter, and c speed of light is 3 into 10 raised to 8. And see, this 3 and 3 can be cancelled, this 3 and this 3 can be cancelled, 4 by 2, that is 2 into 10 raised to minus 11 seconds. Okay, 2 into 10 raised to minus 11 seconds. This is the correct option. Okay. A beam of monochromatic light is refracted from vacuum to a medium of refractive index 1.5, means from rarer to denser medium. The wavelength of refracted light will be smaller, because lambda dash equal to lambda by mu. So it must be smaller, right? And green light of wavelength 5460 angstroms is incident on an air glass interface. If the refractive index of glass is 1.5, the wavelength of light in glass would be. Okay, and see, lambda dash equal to lambda by mu. Lambda is 5460 angstroms and mu is 3 by 2. So that we will get 3640. This 54 by 3 will be 18, and 60 by 3 will be 20 actually. Okay, so 1820 into this 2 will come in the numerator. Okay, 1820. Okay, see, when this 18 is doubled, you will get 36, and 20 doubled, you will get 40. Okay, so it is 3640 angstroms. Two thin lenses of same focal length, but one is convex and the other is concave. When they are placed in contact with each other, the equivalent focal length of the combination will be. See, when two lenses are placed coaxially and in contact with each other, the equivalent focal length capital F is given by 1 by capital F equal to 1 by F1 plus 1 by F2. And here F1 and F2 are equal, but they are of opposite sign. So 1 by F plus 1 by minus F, that is equal to 0. So capital F equal to infinite. Equivalent focal length equal to infinite. Okay. Now, in the figure shown here, what is the equivalent focal length of the combination of lenses? Okay. Now see, suppose we have got two lenses. Those two lenses can be biconvex or biconcave or plano-convex or plano-concave. See, whatever be the order in which these two lenses are combined, the focal length will be the same, or focal length will be independent of the order in which the two lenses are combined. Here I have shown, see, I have two plano-convex lenses. When these two lenses are combined like this, first case, second case, third case and fourth case, see, in all these three cases, the effective focal length is the same. Okay. Now see, we have a biconvex lens at the center and a plano-concave and another plano-concave. See, the combination of two plano-concave lenses is equivalent to a double concave. See, the combination of this plano-concave and this plano-concave, that is equivalent to a double concave lens. Okay, and at the center we have a double convex lens. So this is actually the combination of a double concave and a double convex. And see, this is the expression for the focal length of an equiconvex. Equiconvex means the radii of curvature of both the spherical surfaces are the same. Okay, and see, at the center, for this convex lens, the refractive index is 1.5. Okay, so f1 r divided by 2 into n1 minus 1. So radius is given as 20 centimeter. Okay, so 20 divided by 2 into n1, that is 1.5 minus 1, that is 0.5 into 2, that is 1. So f1, that is equal to 20 centimeter. See, focal length of this biconvex or equiconvex lens at the center, that is 20 centimeter. And see, for a biconcave lens or equiconcave lens, means the radii of curvature of both the spherical surfaces are the same and both are concave, then it is called equiconcave, and its focal length is given by, see, r divided by 2 into n2 minus 1, where n2 is the refractive index. This is for equiconvex and this is for equiconcave. The only difference is the negative sign. Okay, radius is again 20, but the refractive index is 1.6 minus 1, so it will be minus 20 by 1.2. Okay, we have to get the effective focal length 1 by capital F equals 1 by f1 plus 1 by f2. That is 1 by 20 plus minus 1.2 by 20. So it will be minus 0.2 by 20, or it is minus 1 by 100. So effective focal length will be minus 100 centimeter. Okay, minus 100 centimeter. So this is the correct option. Right? Now a biconvex lens has radii of curvature 20 centimeter each. Means it is an equiconvex lens. If the refractive index of the material of the lens is 1.5, the power of the lens, power is reciprocal of focal length, provided that focal length must be in meter. Okay, and P equals 1 by F. See, F is actually R by 2 into mu minus 1. So 1 by F will be 2 into mu minus 1 divided by R. Okay, so mu is 1.5 minus 1, radius is 20 centimeter, but it should be expressed in meter in order to get the power. Okay, so 20 centimeter is equivalent to 0.2 meter. So we will get see, 1.5 minus 1 is 0.5 into 2 is 1. 1 by 0.2, that is 5 diopter, and it is positive. So this is 5 diopter positive. Okay. Now next, a convex lens capital A of focal length 20 centimeter and a concave lens capital B of focal length 5 centimeter are kept along the same axis with a distance d between them. If a parallel beam of light falling on A leaves B as a parallel beam, means, see, when a parallel beam is passed through this combination, after refraction through both the lenses, the beam will converge to the focus, and that focus is the effective or equivalent focus of the combination. Here, after refraction through both the lenses, the rays are rendered parallel, means they will not converge, or they will converge only at infinity. So the effective focus is at infinity and the effective focal length is equal to infinite. Okay, and see, this is the expression for the effective focal length when two lenses are kept coaxially at a certain distance d apart. Okay, 1 by capital F equals focal length of this is f1 and this is f2. Okay, the separation between them is small d. See, this is focal length f1, this is focal length f2, and the separation between them is small d. Okay, so the effective focal length capital F is given by, okay, here the effective focal length is infinite, here capital F is infinite, so 1 by capital F will be 0, 1 by F equal to 0. So on the left side it will be 0. So when this minus d by f1 f2 is taken to the left, it will become plus. So d by f1 f2 will be 1 by f1 plus 1 by f2. Okay, and d we will get d equal to f1 plus f2. See, focal length of the first lens is positive because it is convex, and focal length of the second lens is negative because it is concave. Okay, so plus 20 plus minus 5. So it will be 15 centimeter. Okay, so the separation between the two lenses in this case is 15 centimeter. An equiconvex lens has power P. It is cut into two symmetrical halves by a plane containing the principal axis. Okay, the power of one part will be P only. Okay, see, this is the lens and it is cut by a plane containing the principal axis. Means it is cut like this. This is one half. Okay, its radius is not changed. Its refractive index also does not change. Okay, so power will remain same. Okay, so when it is cut into two halves like this, power will remain unchanged. Okay, when it is cut into two halves like this perpendicular to the principal axis, then the focal length will get doubled and the power will become half. Okay, in this case, see, this is the way it is divided into two, so the power will remain same. So P. Now a lens having focal length f and aperture diameter d forms an image of intensity capital I. A aperture of diameter d by 2 in central region of lens is covered by a black paper. Focal length of lens and intensity of the image now will be, see, focal length, formula for focal length is given by 1 by f equal to mu minus 1 into 1 by r1 minus 1 by r2. If you cover the central portion of the lens with a black paper, there will not be any change in mu. There is no change in r1 or r2. So the focal length will not change. Power of the lens will not change. Okay, so focal length remains same. Now see, the intensity is proportional to square of the diameter. When half of the aperture is covered, 1/4 of the intensity will be lost. Okay, so the intensity of the image formed after wrapping the central portion with a black paper will be only 3I by 4. 3I by 4. Okay, because half of the, see, intensity proportional to square of the aperture. When half of the aperture is covered, 1/4 of the intensity will be lost. Okay, because intensity proportional to, see, I intensity proportional to diameter square. Okay, so 1/4 intensity will be removed. Okay, will be lost. So the remaining intensity will be only 3I by 4. So F and 3I by 4. This one. Okay. A convex lens is dipped in a liquid whose refractive index is equal to the refractive index of the lens. Okay, so there will not be any refraction through that lens. Okay, so remains unchanged, becomes 0. What becomes 0? Then its focal length. Focal length becomes 0, becomes infinite. That is true. Becomes infinite means it will not converge. It will not converge. Now a plano convex lens is made of a material of refractive index 1.6. The radius of curvature of the curved surface is 60 centimeter. Focal length. See, for plano convex lens, focal length is f equals r by mu minus 1. Okay, if it is an equiconvex lens, r by 2 into mu minus 1. Okay, if it is plano convex, r by mu minus 1. If it is equiconvex, means both the surfaces are convex and they are of equal radii. Okay, then r by 2 into mu minus 1. Here we have a plano convex. So r by mu minus 1 we have to use. R is 60 centimeter. mu is 1.6. So we will get 100 centimeter. So focal length is 100 centimeter. Okay, and a convex lens of focal length 80 centimeter and a concave lens of focal length 50 centimeter are combined together. What will be their resulting power? See, P1 equals 1 by F1 provided that F1 is in meter. So it is 1 by 0.8 and it is equal to 1.25 diopter positive. And P2 that is 1 by F2 as it is a concave lens. See our focal length 50 centimeter means 0.5 meter minus 2 diopter. When these two are put in contact coaxially, then the effective power P equals P1 plus P2 and it is minus 0.75 diopter. Okay, minus 0.75 diopter. Focal length of a convex lens of refractive index 1.5 is 2 centimeter. Focal length of the lens when immersed in a liquid of refractive index of 1.25 will be. See, F is the focal length in air and F dash is the focal length when immersed in a medium of refractive index mu dash. Mu is the refractive index of lens and mu dash is the refractive index of the medium in which the lens is kept. See, when it is in air, its focal length is F. When it is kept in medium, its focal length is F dash. So F dash by F equals mu minus 1 divided by mu dash minus 1. Okay, mu is 1.5 and mu dash is 1.25. Okay, this is 1.5 minus 1.5. It can be written as 1 by 2. 1.5 by 1.25 is 6 by 5. 6 by 5 minus 1, that is 1 by 5. Okay, so it is equal to 5 by 2. So F dash will be 5 by 2 F and F is the focal length in air. It is given as 2 centimeter. So focal length when kept in a medium of refractive index 1.25 will be 5 centimeter. Okay. The refractive index of the material of a prism is root 2 and the angle of the prism is 30 degree. One of the two refracting faces of the prism is made mirror inwards by silver coating. A beam of monochromatic light entering the prism from the other face will retrace its path. See, path can be retraced only from a mirror where it is incident normally. Okay, so here is the ray incident on the first surface at an angle I. Okay, it suffers a refraction at the first surface. Okay, that refracted ray must be incident on the second surface normal to it. Then only it can retrace its path. If it is incident normally, so this angle must be 90 degree. Okay, here we have, this is the angle of the prism. It is given as 30 degree. See, this is 30 and this is 90 degree. How do we know that it is 90 degree? Because the ray must be incident normally on this surface. Okay, then see, this is 90 and this is 30, so this must be 60. Okay, and see, this is the normal. Okay, so this must be 30, that is the angle of refraction at the first surface. Okay, angle of refraction is 30 degree. Now again, let us apply the general form of the Snell's law of refraction. See, outside the prism, the medium is air and its refractive index is 1 and sine of the angle there, sin I. See, inside the prism, refractive index is mu and the angle we have got 30 degrees, so sin 30. So sin I, see, mu is given as root 2 and sin 30 is 1 by 2. So we will get sin I equal to 1 by root 2. Means I is 45 degree. Now we have a thin prism having refracting angle 10 degrees made of glass of refractive index 1.42. This prism is combined with another thin prism of glass of refractive index 1.7. This combination produces dispersion without deviation. The refracting angle of second prism should be. See, without deviation. Actually, see, deviation produced by a small angled prism is mu minus 1 into A. Okay? Or let us say mu dash minus 1 into A dash. That is the deviation produced by one prism. Okay? Mu minus 1 into A. This is the deviation produced by the other prism. If there is no deviation, means dispersion without deviation. Without deviation means the resultant deviation is 0. This is equal to 0. Okay. So from here we will get A dash equal to mu minus 1 divided by mu dash minus 1 into A with a negative sign. Okay. And mu is 1.42 and mu dash is 1.7. So it will be 0.42 divided by 0.7, or you can write it in simple ratio 42 by 70 means it will be you can divide it with 14. So 3 by 5. Okay, so 3 by 5 into 10, that is minus 6 degree. And that negative sign is to show that the prisms must be combined with their refracting angles pointing in opposite directions. See, if you take one prism like this, then the second prism should be combined with the refracting angle pointing in opposite direction. Okay, so we will get minus 6 degree. Okay, the second prism should be of angle 6 degree. Okay. The angle of incidence for a ray of light at a refracting surface of a prism is 45 degree. Okay. The angle of prism is 60 degree. If the ray suffers minimum deviation through the prism, the angle of minimum deviation and refractive index of the material of the prism respectively are. Okay. Now, when the prism is in minimum deviation position, angle of incidence I equals A plus D by 2. Okay. And that I is given as 45 degree. Okay. And angle of prism capital A is 60 degree. So we will get this D angle of the minimum deviation equal to 30 degree. Now we have to get the refractive index. Mu is sin I by sin R. And in minimum deviation position, R equals A by 2. A is 60 degree, A by 2 is 30 degree. Okay, and angle of incidence is 45 degree. Sin 45 by sin 30. Okay, so mu is root 2. Okay, so 30 degree and root 2. So 30 degree and root 2. Okay. The refracting angle of a prism is capital A and the refractive index of the material of the prism is cot A by 2. The angle of minimum deviation is, okay, mu equals cot A by 2, means cos A by 2 divided by sin A by 2. Okay, cos A by 2 you can write sin 90 minus A by 2. Okay, so sin 90 minus A by 2 divided by sin A by 2, that is the refractive index. And the general formula for refractive index of a prism is mu equal to sin A plus D by 2 divided by sin A by 2. So we have two expressions for the refractive index of the given prism. Okay, one is sin 90 minus A by 2 by sin A by 2 and the other is sin A plus D by 2 by sin A by 2. See, the denominators are equal. So you can equate the numerators. Sin A plus D divided by 2 equals sin 90 minus A by 2. Means A plus D by 2 equal to 90 minus A by 2. See, multiply this equation throughout by 2. On the left side you will get A plus D. On the right side first term will become 180 and second term will become A. Okay, so D will be, take this A to the right, so we will get 180 minus 2A. 180 minus 2A. So this is a beautiful question. Okay. Now next, a beam of light consisting of red, green, blue colors incident on a right angled prism. The refractive index of the material of the prism for the above red, green and blue wavelengths are 1.39, 1.44 and 1.47. See, a beam of lights. See, mu equal to 1 by sin C. Okay. And when mu equal to root 2, C equal to 45 degree. Okay. Here, see, when light is incident, normally on this vertical side, light is incident normally. So it travels undeviated through these vertical sides. Okay. And at this side, okay, light tends to travel from glass to air. Okay, where the angle of incidence is 45 degree. Okay, here light tends to travel from glass to air where the angle of incidence is 45 degree. If that 45 is more than critical angle, total internal reflection will take place. Okay, if that 45 degree less than critical angle, it will get refracted, means it will emerge out of the prism. Okay, let's see. When mu equal to root 2, then critical angle is 45 degree. For green and blue, see refractive index, refractive index for red, green and blue. Root 2 is 1.414. See, this is more than 1.414 and this is also more than 1.414. So for green and blue, refractive index is more than root 2. Okay. So critical angle will be less than 45. For blue and green, critical angle less than 45. Here the angle of incidence is 45. So blue and green will suffer total internal reflection. Blue and green will suffer total internal reflection, but red will emerge. Now see, a narrow beam of light is incident on this inclined surface at 45 degree. That narrow beam consists of red, green and blue lights. Okay. Now this is the situation. See, this is the narrow beam with the red, green and blue. See, this green and blue will suffer total internal reflection and get reflected along the same line. But the red ray will be emerging along a different line. Okay, emerging out of the prism. Okay, so red will be separated from green and blue. Let us check. Separate all three colors, that is not possible. Not separate the three colors at all, that is also not true. Separate the red color part from green and blue colors. Okay, that is true. Okay, separate blue color, that's false. Okay, now let's see what we have next. This is also a wonderful question. Angle of prism is capital A, one of its refracting surfaces is silvered. Light rays falling at an angle of incidence 2A on the first surface returns back through the same path after reflection at the silvered surface, means the ray should be incident on the silvered surface normally. Okay, so this is the incident ray, it suffers refraction here and incident normally on this surface. Okay, then after reflection from this surface, it retraces its path. Okay, now see, we have this is the angle of incidence 2A. Okay, this is the angle of refraction A. Okay, how do we get that A? See, here we have a triangle here. Okay, this is the angle of the prism is A and this is 90 degree. Okay, in a triangle the sum of these three angles must be 180, of which this much is 90 degree. Okay, so the sum of these two must be 90. Okay, sum of these two must be 90, right? Okay, see, this is given as A, so this must be 90 minus A. Okay, and see, on this surface this is normal. Okay, so the total angle must be, this total angle must be 90, of which this much is 90 minus A, so this angle will be A, right? See, this is 90 minus A, so the remaining this will be A. Okay, so angle of incidence is 2A, angle of refraction is A, right? And mu, refractive index is sin I by sin R. Angle of incidence is 2A and angle of refraction is A. So sin 2A divided by sin A. See, this sin 2A is 2 sin A cos A divided by sin A. 2 sin A cos A divided by sin A, that will be 2 cos A. Okay, so we will get 2 cos A. This is the refractive index. Okay. Rainbow is formed due to a combination of dispersion and total internal reflection, right? Now see, the refractive index of the material of a prism is root 2 and its refracting angle is 30 degree. One of the refracting surfaces of the prism is made mirror inwards. A beam of monochromatic light enters the prism and retraces from the mirror surface if its angle of incidence of the prism is. See, here we have the prism, angle of the prism is 30 degree. Okay, And see, the ray should retrace its path after reflection from the second surface. Means this ray should be incident on the second surface normal to it. So this is 90 degree and this is given as 30. So this angle will be 60 and the angle of refraction will be 30. Okay, refractive index is given as root 2. Let's apply the Snell's law in general form. Okay, refractive index outside is 1 and the angle of incidence is I. So 1 into sin I. Refractive index inside is root 2 and the angle of refraction is 30 degree. So root 2 sin 30. So I we will get 45 degree. Okay. An astronomical telescope has objective and eyepiece of focal length 40 centimeter and 4 centimeter respectively to view an object 200 centimeter. Away from the objective, the lenses must be separated by a distance. See, objective is at a distance 200 centimeter from the objective. Okay, so let's find the image distance of the objective. 1 by VO. VO stands for image distance of the objective, minus 1 by UO. UO, object distance of the objective, is minus 200 centimeter. That is equal to 1 by FO. FO, focal length of the objective, is 40 centimeter. And VO we will get 50 centimeter. Okay, and see, when this is in normal adjustments, see, the image formed by the objective will be at the focal plane of the eyepiece, or from the image formed by the objective, the distance of the eyepiece will be equal to its focal length, means FE. Okay, so separation of the two lenses will be from here to here. This is VO, image distance of the objective, plus focal length of the eyepiece. Okay, so VO plus FE. Okay, and VO we have got 50. FE is equal to 4 centimeter. So the separation between the lenses is 54 centimeter. 54 centimeter. Okay. The magnifying power of a telescope is 9. When it is adjusted for parallel rays, the distance between the objective and the eyepiece is 20 centimeter. Okay, the focal length of the lenses are, see, FO plus FE is the separation of the lenses, it is 20. And FO by FE is the magnifying power, it is 9. Okay, so we will get, see, FO equals 9 FE. FO equal to 9 FE plus FE, that is 10 FE equal to 20. So FE will be 2 and FO will be 18. Okay, FO 18, FE 2. Okay, FO 18 and FE 2. Right.